Now, can everybody hear my or see my screen?
Okay.
Yeah. Wait, hang on. No, I haven't shared yet. Excuse me. So here we go. Can you see my screen now?
Very good.
Okay, thanks. All right, let me see here. So let me start this presentation. Okay, see if this is going to work. Yeah, so I decided to cover this topic because these are very highly efficient amplifiers. They're, as you can see there, they're over 90% efficient. And we're used to working with stuff that's a lot less than that. So I was intrigued by, learning this, and I figured I'd talk about it because I wanted to know basically why not everybody's got a Class C amplifier in their radio instead of the type of linear amplifiers we commonly use today. So I thought I go over. I just introduce you all to what they are, and there's basically actually three types of amplifiers in this category. There's Class D, Class C, and Class F. I'm not going to cover Class F because we're barely probably have enough time to cover Class D and E. But I'll just talk about the Class D and E amplifiers. And Class D, I should say Class C is really just kind of a variation on Class D. So I think, yeah, just sit back, grab a coffee or whatever, and I hope I don't put you to sleep with this stuff. But it's something that you might want to be aware of because it may be something that might be more common in the future for amateur radio use. All right, so with that, the basic premise is that, well, first off, let's just jump back here. So the concept of it really was invented back in the 30s, and it really wasn't the amplifier per se. It was really more the concept of modulating this amplifier. And so there was this person by the name of Alec Reeves, who's from England, who pioneered what he called pulse code modulation back in the 30s, and ended up getting a few patents for it, and one in France, I think one in the UK, and also a US patent in 43. So it was the first real attempt of actual signal processing where signals get sampled, digitally. And you've all heard of, say, digital to analog converters or analog to digital converters, really. So this would be the first idea of an analog to digital converter where you take a sine wave and then sample it, every, say, portion of the wave, maybe every tenth of a wave or 20, some fraction, and then you do that continuously, and you can reconstruct the entire sine wave without actually getting a actual sine wave. You can actually do this digitally by pulsing, mixing a pulse signal with the sine wave, and then just generating a bunch of pulses that have varying amplitudes that follow the sine wave pattern. So he developed this back in the 30s, and it's been pretty much what we have today for a lot of signal processing applications. And Class C amplifiers originally were this concept. They were actually started to be used and built in the 1950s, but because it was very difficult in those days with the technology of the time to make them work properly, they were abandoned. So the idea of them has been around for quite a while, and what they basically are like a switch mode power supply. You basically have a couple of transistors that are switching constantly, and you are using that switching to generate your signal. Now you have to modulate the switching, and I'll talk about how that's done. But basically that's what they are. And so the idea is that when you have a switch mode, either a power supply or amplifier, and there's really very little difference, that the efficiency is extremely high because the transistors generate very little heat during the switching process. They don't, when they conduct current, the voltages are very low because they're in saturation mode. And in saturation mode, the voltage across the transistors is low, but they're conducting a lot of current. So the power that is being actually generated is very low. I should say there's a lot of current, but I'm talking about internally. So there's very little dissipation of heat. And when they're off, so they go on and off. And when they go off, their current, they're not conducting any current, and their voltage goes back up to being, say a high level. But since there's no current being, generated there, again, there's no current. Oh, sorry, there's very little power, power dissipation. So the transistors don't get hot. You see, like a regular linear amplifier, either the vacuum tube or transistor will get very warm because they're constantly conducting current. And I'll show you, a graphic about all that. So the efficiency can really be close to 100%, and that's the theory. But in reality, they are over 90% efficient. So they're quite efficient devices. Nowadays, instead of this pulse code modulation, which was similar to pulse width modulation, we use pulse width modulation and pulse, actually I called it pulse density modulation, but it's really pulse frequency modulation. And these are the techniques to modulate the pulses to generate the actual sine waves. Okay, so let's get into what's going on there. Oops. Okay, so just kind of recap or reviewing the more traditional amplifiers. We all know about basically Class A amplifiers. These are the traditional linear amps. They could also be Class B and Class AB types, which are, but they're basically Class A amplifiers. Their efficiencies are very low. As you can see, they're usually 25, 30%, and occasionally a little bit higher than that, but not much. So these are really the types of amplifiers we may be having in our radio, especially the older radios and older amplifiers would be using Class A types of amps. And so they're very inefficient. They get very warm. Okay. And, this goes back into the 50s. So primarily they were used for AM and sideband. The improvement over Class A is Class B, because those are push-pull type amplifiers. We have two tubes or two amplifiers, two transistors that are working in tandem, but they're working in a push-pull mode, which means that when one is conducting, the other is not. And then that increases the efficiency by quite a bit over Class A. And in theory, you can get up to 70% efficient or better using a Class B amplifier. However, their audio characteristics are not very good. They have a lot of distortion, and not just audio. They're basically they're not very pure. They don't generate pure sine waves because of technical issues at the crossover point when one say transistor is conducting and the other is not in a switch. There's a crossover point where they're going through 0 volts in the sine wave, and usually there's some sort of discontinuity there. So it creates some sort of distortion, and there's ways of getting around that. But they're not typically they're efficient, but not that bad, not that efficient. So again, they're used mostly for sideband and AM types of modulation. Now, Class C, if people recall what Class C is, it's where the device, meaning the vacuum tube or the transistor, will conduct only maybe a small portion of the sine wave. So what happens is the Class C amplifier will actually pulse, and so they're not linear, but they the pulsed waveform can be transformed to a regular smooth sine waves waveform by filtering, and but because of that, it's very difficult to get them to be modulated with, say, voice. So they're mostly now used for, well, if they're used at all, they're used for in CW transmitters or FM transmitters. So types of modes where there's continuous say a continuous waveform and there's no amplitude modulation going on. So so those are efficient amplifiers, Class C, but again, you can't use them for sideband, you can't use them for AM. So in comes Class D. Oh, excuse me. So Class D amplifiers, when I'm showing here a graphic here, and what this graphic is kind of showing is recapping what I've said. This is on the y-axis, you get the dissipation of power for different loads. And what this basically is showing that Class A dissipates a heck of a lot of power compared to, say, Class B, and Class D is well below even Class B, except under certain load conditions. So you can still get away with getting fairly comparable efficiencies of these kinds of amplifiers, depending on the particular conditions you're using. Right now, Class D amplifiers are really popular in audio amplifier applications. So this picture here shows a speaker, but you can, also just sort of imagine this being used for RF applications, and you get the instead of a speaker, you have an antenna there. But what you're doing is you are creating just basically pulses that are being modulated and then filtered to generate a sine wave. So the main point is that the transistors, which are, I don't know if you can see do you see my cursor at all? Or is that just me? Okay, nobody sees my cursor. Okay, sorry, I can't point it out.
It's there, it's small.
What's that?
It's there, it's just kind of small.
Oh, okay. Yeah, I wish I could increase its size. But anyway, these transistors, which are kind of noted as MH and ML, those are the switching transistors. And those, the point here is that they don't generate any heat or very little heat. And so that's where the efficiency comes in. But they are able to put out lots of power. So they can drive speakers and audio applications or antennas. And let's get into the reasons why. Okay. All right. Here we go. So this plot here shows the efficiency that you can obtain. So class A, B, and D are compared here. And I guess the graph speaks for itself. Where the power going to the load is as that goes to the maximum value that the load can take, that's where the efficiencies start to merge. But in most applications, you're down far lower into load ranges that are or I should say powers going to load that are far less than what the load is capable of. So there you get a big differentiation in the types of efficiencies you can achieve by these different amplifiers. All right, so what's going on actually? So all right, this graph here on the left shows that when a transistor is conducting, it's as its current is, say on the left side of the graph here, when the current's at its maximum, its resistance is down at a minimum, and then when it's not conducting, its resistance is at a maximum, and then it's the amount of current that can go through it is at a minimum. So the transistor acts as kind of a variable resistor. And then, so what's going on is as a sine wave is traversing through this transistor, or I should say a sine wave is being applied to the transistor, the power that the transistor is consuming or dissipating is going sort of cycling through this little hump here that's labeled PD. And it's continuously going back and forth like that. So the transistor is at the extremes, not generating or dissipating much power, but it goes through a peak where the power that's dissipating is maximal. Okay, so it's this is in this region here is where you get a lot of heat generation. Okay, that's a linear application here. Now in a switching application here on the right, again, you get the same type of curve, except what's going on is the transistor is not smoothly going through the middle phase. So what's going on is it's going from the on state to the off state and back and forth like that. So as it's doing that, it's spending very little time in the middle. So it's either on or off, and in either case, it's a lot of currents running through the transistor, but the voltage is very low, or there's no current at all running through the transistor and the voltage is higher. So in the on state here, this is like a square wave form of the voltage. So here you got a square wave on where the voltage is at its maximum, but there's very little current flowing through it. And then and then in the off state, there's no current flowing through it at all. I'm sorry, in the on state, there's a lot of current flowing through it, but then the transistor's sort of in saturation, so it's not consuming power. It's not consuming power in the off state. It's only really consuming power in the transition states. So when it's transitioning from on to off and off back to on, that's where the power is being really consumed. And as you can see, the amount of time it spends doing that is very small. So it's not really consuming any power. compared to the time it's on or off. So if you look at it, another sort of a way of seeing that is if you see the on-off state, here's the in the middle, the graph here is showing the current that's going through during these states, but the power that's being consumed is like these little is only occurring at the transition states. So the amount of power is like a little teeny pulse compared to the on-off parts of the Diddy cycle, and then therefore there's very little power that's actually being consumed. Here's sort of a very simple schematic of what a Class D amplifier looks like. So we can understand in this section here the switching part a little bit, but the main thing is how the heck do you modulate this thing? Because what the switching does is create this square wave, and then you think, well, what the heck's the use of that? It's kind of like the switching power supply, where in a switching power supply application, you're doing the switching to generate the to be able, well, basically what the switching does is increase the frequency of the power that's coming in that you want to increase or decrease, and then you're sending that through a transformer, which is small compared to like a linear or transformer used in a linear power supply, and that's a whole different thing. But the thing is, you don't really modulate the square wave. In this kind of a case, you want to modulate the square wave because what you want to do is you want to create a sine wave out of that. Okay, so what's done is you have an input which is like, say, this little sine wave here, which is sort of like let's say the voice, coming through a microphone, and then that goes to a comparator. That's this, this device here, and then also on the other input of the comparator is a triangle wave, or it could be it could be a triangle wave, it could be a sawtooth wave, but something like that. And what goes on is that in the comparator, let me jump to the next slide. Oops. Sorry about that. Here. Okay, so in the comparator, what we're doing is we are combining sort of the sine wave here in green, and then here the triangle wave in blue. And what the comparator is looking at is like, when is one signal greater in voltage than the other signal? Okay, so let's say it compares on the first cycle of the triangle wave here. It's looking to see that it sees that the triangle wave is actually larger than the sine wave. Okay, so it's going to put out, say, a maximum pulse, and that would be here. I'm pointing at the first square wave, or the first pulse in the square wave train. Can everybody see that? Okay. All right. The next half cycle, then the comparator sees that the triangle wave is lower than the sine wave. So now, instead of putting out like a plus 5 volt wave or square wave, it's now going to put out maybe a minus 5 point or a 5 volt, or maybe a 0 volt. So you get this, you get the square wave generated according to the difference between the sine wave and the triangle wave. And what that does is, because the amount of time that the triangle wave is intersecting or not intersecting the sine wave, it'll change the width of the pulse. So you can see, if you look down at the square wave pulse train here, you can see that the width of the pulses is changing according to where the sine wave is. And so what's happening is you develop a pattern of these widths that actually follows a sine kind of a curve. Now, if you filter this, you'll actually get the green line down here, which follows this almost the exact same sine wave that was compared to the triangle wave, but it's got this ripple in it, and it's also inverted. However, you recover the sine wave, and then you can imagine, once you've done that, you can filter it further to get rid of the ripple. So again, this is kind of another view of that, where the pulse pattern, in this case, this would be I think a pulse frequency modulation, where now you're not modulating the width of the pulses, but you're modulating the frequency of the pulses. So that can change according to what the sine wave is doing. This is a pure sine wave. Now you can imagine if you modulate the sine wave, say with them like amplitude modulation, then it'll be a the pulse train will follow a more complex sine wave, but it will still follow the sine wave. So it's the amplitude of the sine wave that will determine, say, the frequency of the pulses in this case, or in the previous slide, the width of the pulses. So once you've done that, this would be a picture of something where you get repeated, a repetition of the sine wave of the pulse. In this case, I think this would be a pulse frequency modulation, where you get something that almost looks like a frequency modulated wave. But in this case, it's just a bunch of these pulses that are either bunched together or spread apart, depending on whether the sine wave is positive or negative. So the positive, say the positive portion of the sine wave would cause the pulses to bunch together, and the negative swing of the sine wave would cause the pulses to to move apart from each other. Where the maximum, or I should say the minimum of the sine wave would occur, like the biggest separation between the pulses, and the maximum of the sine wave would occur where you get the most dense, I guess, bunching of the pulses, if you want to call it that. And I think down here in the green is a similar kind of a display, but this time it's for pulse width modulation. So the end result is you get again this kind of a pattern, just zoomed in. And the deal is, so how can you get the sine wave recovered from this? Okay, so actually, it turns out that if you did say a Fourier transform, or just look at the frequency spectrum of those kinds of pulses, you'll see that you get a whole bunch of harmonics, but you do have a fundamental occurring. Say, in this case, I think it's 5 megahertz. So it would be this first peak here. And if you can build a filter that can get rid of all the harmonics and just say a low pass filter that can just get this peak, or a band pass filter, then you can recover the sine wave. So when that's done, you get something like that. So in blue, you can see that the sine wave is recovered. It's superimposed on the pulse width modulated pulses there. But you can see that the initial sine wave is there, but it has a lot of noise in it. It's got a lot of digital noise. If you want to call it ripple, that's kind of what it is. So if you filter that further, you'll get a pure sine wave out of that. So let's see, which way am I going here? No, back this way. So yeah, okay. So here's an example of just a recovered sine wave where you get it's got ripple in it, but it's there. It's inverted from the original sine wave, but it is there. Okay, it's recovered. And there's other modulation techniques where this is down here below is schematic of a circuit of a Class D amplifier that uses 4 switches. These are the switches over here, 1, 2, 3, 4, and this is what they call an H bridge type of configuration. But each switch is operated in opposition, so you get the switch. It's similar to if you've ever seen or a schematic for say a switch mode power supply. It's similar to that. But what this allows you to do, if you take the modulation and feed it into the first comparator, and then you invert the modulation and put it into another comparator, you can actually get a pattern which is shown up here in green. So you get these like positive and negative peaks. The advantage here is that this one allows you to have no current flowing through the load when there's no modulation. In other words, when there's no, say, voice modulation. In the previous example, I don't have a schematic to show that, but it will allow current to constantly flow through the load. So you lose efficiency that way. But in this type of modulation scheme, we have the modulation and inverted modulation. Then you get area. You can actually have 0 current going through the load when there's no voice modulation going on. So it actually increases efficiency even further than the previous design I showed you. So this is where you can get efficiencies that are very close to 100%. Okay, so there's basically a couple of different topologies that people have used for Class D amplifiers. And One is a voltage switching circuit, and the other one's a current switching circuit. I won't go into the details. The only thing is that the filter, what's used is actually before the load. There's a LC circuit right here. This is a series one for voltage switching supplies or amplifiers, and there's a parallel type of LC circuit that's used in current switching. There's advantages. There are advantages of current switching over voltage switching, but they're a little bit off topic right now. So the let me see. I think I'll skip that. So the filtered output eventually does look pretty much like a very nice sine wave, and in this case, the sine waves are unmodulated. So, but they are definitely modulatable. Where instead of, if you look at the schematic right here, the source is a pulse, just simply a pulse generator. But as pulse generator can be modulated by say amplitude modulated, then the wave in green here would be an amplitude modulated wave as well, and that is the actual waveform that gets output to the antenna. So this slide here just summarizes the different topologies. So you basically have your voltage switching topologies, your current switching topologies. There can be a minimum two switching devices. And these are transistors usually, switching transistors in either voltage switching mode or current switching mode. And there's different ways you can couple the power from the switching circuit into the load circuit, which is just another name for the antenna. And in some cases, you can use actually 4 transistors, which will actually give higher power than just 2. So that's the basis now of Class D. Now for Class E, there's a similar type of situation. However, what is done in Class E is instead of 2 transistors switching, you can have a single transistor switching, which already makes it a little bit of a simpler circuit to work with. The main thing here is that what they've done is building this in the middle here, this LC circuit. It's supposed to be a filter and also an impedance matching impedance matching circuit. And what is done here, typically the impedance matching part and the filtering part are designed for the actual frequency of operation of the switch here. So if you want, say, a 7 megahertz signal coming out, then you would switch the transistor at 7 megahertz. I should say the pulse generator would operate at 7 megahertz pulse rate. But in this case, what they've done is they've actually changed the frequencies a little bit. They make them a little bit the frequency input to this LC circuit and the frequency output, or actually the match is designed for a different frequency than the actual driving frequency. So what that allows to happen is that this is a little bit difficult to follow, I understand, but during the on-off switch or phase, let's say in the off position, the voltage that's going through the transistor goes to this sort of rise and falls back down. But the main point is that in the transition regions, which are where you transition from on to off, the voltage is 0, either for going from on to off or going back from off to on. And the current is doing a similar thing. It's not 0, but it's less. Okay, the current at the transition points is less than the maximum current. So there's more power savings involved with Class E than with Class D. So Class E amplifiers are actually more efficient than Class D. And these are some topologies of circuitry that are used. So already, if you recall from the Class D, there was always at least 2 switching transistors involved. Here, you only need 1. So the circuit's a lot simpler. I mean, they're literally this simple. And you can have a topology where you have 2 switching transistors involved. And this looks more like a Class D or even a Class B type of amplifier. but it's designed so you can actually generate more power than you can get with a single transistor here. So the advantages, the Class C is even more efficient, and you can actually generate a little bit more power using the dual switching topology. It's a little bit weirder as far as the waveforms are concerned, but the idea is that again, you get very interesting behavior at the transition points, because the voltage in green here shows that the peaks are showing the voltage as it changes during like when the on time of the pulse. It starts out at 0, goes through a maximum, comes back down to 0, and goes through then the transistor is off. When the transistor turns back on, its voltage is 0, and then it goes through its peak of voltage. But at the peak of voltage, the current, it's only there for a short time, so the amount of power and actually the current going through, if you look at the blue curve, is actually 0, because this is actually kind of a negative pulse of current here. So when the transistor is actually turned on, the current is practically 0 going through it, and then when it goes through sort of a rise when the transistor is off, which is kind of strange. But the main thing is that the current is either 0 or less than maximum when it's going through its transition from on to off and off to on. So in that case, combined with the fact that the voltage is 0 at the transition points, you get practically 0 power dissipation. So that's really it. I know it's kind of technical, but that's really the essence of how these kinds of amplifiers behave and why they're so efficient. So then the big question is then, to me, is like, okay, with all these advantages, so why aren't we seeing more of these things actually being used? And that's actually a question, because they are at this point experimental. Well, first of all, let's look at the pros and cons of Class D and E type of amplifiers. They're very narrow bandwidth amplifiers compared to the other types that we commonly use today. So that's due to the fact that you have to filter so much to get rid of all that ripple and digital noise that's actually sort of inherent in that sinusoidal signal. And in order to put the signal out on the air, you can imagine you can't have any of that or almost hardly any of that left in your final output signal. But and because of the fact that they're narrow bandwidth, they can only be used really, if you build one, you can only really use it on one band. So it wouldn't be a multi-band amplifier that you can use, from 160 to 10 meters. But they're so cheap to build, because if you recall what the schematics only have a few parts in them. I mean, it's a little bit more involved than that in reality, but they are pretty cheap to make. So you can actually make a multi-deck amplifier where each deck would be for a particular band, and you can switch between these decks, and you can combine them into one unit, and then you have an amplifier that can go on several bands. So have people built any of these things for ham radio? The answer is yeah, but very few, primarily because of the fact that Class D and Class E amplifiers are not well known in the RF world. They're mostly used right now as audio amplifiers for the same reasons, because you can get a lot of power out of these things with very high efficiency and very little heat generation. So right now, people have built AM and CW amplifiers, and you can find a few examples of these on YouTube. For sideband, and this is probably the Achilles heel of these kinds of amplifiers for ham radio applications, they're not as easy to implement, because basically you have to do all the tricks to make sideband happen at high power. Right now, if you have a regular Class A, Class B, or Class C amplifier, you can, well, actually not Class C, Class A, let's say, linear amplifiers, you can create the sideband signal at an earlier stage than the actual power amplifier stage, so at low power. You can modulate your signal or your carrier, then filter the carrier to get rid of the, I'm sorry, filter the modulated carrier to get rid of the pure carrier and one of the sidebands, and then you send the desired sideband out to the power amplifier. In the case of Class D and Class C, you can't do that because you have to modulate your, as I showed you, in the beginning, you have to modulate the triangle wave or the sawtooth wave with a sine wave, which is usually amplitude modulated. So you're going to end up with an amplitude modulated amplified wave. So once that wave is amplified, then you need, if you want to get sideband out of that, you're going to have to filter as an amplified wave. And that's a little bit more tricky because the components you would need to do high power filtering are going to be a lot more expensive and so forth. So sideband so far, as I've seen, has not been implemented. It's only primarily AM. And they can be used for CW because if you're not using an amplified carrier, you can just turn the carrier on and off when you key down and key up for CW. But for AM, that's primarily where the money is right now for these kinds of amplifiers in ham radio. But nobody's built one commercially yet. These are experimental ones. So let's see. So examples that I think the best example is this guy here, VK3HN, who's built a couple of these now. So he's got like a 200-watt Class D amplifier for AM, and he's built a 120-watt one, as you can see here, for 40 meters. But he and others have combined multiple decks, like I talked about before, where you can build an amplifier for a particular band, and even then, it's probably going to be limited within the band in any case, because the filtering has to be so tight that some tricks have to be played to actually be able to span a full band with some of these. So, but you can reach fairly high power, and they're not expensive, relatively speaking, to build. Here's another example here for a 100-watt amplifier, 160 meters. So these are done, but these are the only examples I could find on YouTube of these kinds of amplifiers for ham radio purposes. So the field is pretty wide. I would say the field for experimentation for this kind of an amplifier is pretty wide. So the motivation would be really high efficiency. You could probably make smaller amplifiers at high power because the parts are relatively small, and you don't need a lot of heat sinking and so forth to be able to handle the thermal or do the thermal management with Class D amplifiers. And also the same goes for Class C amplifiers. So here's an example of that same Australian ham VK3HN who built now a Class E amplifier for 160 meters. And that's kind of an example of his work there. The most complicated part being the modulation. But once you get these things to work, they work very well. All right. So anyway, I just wanted to make an introduction to you guys to these types of amplifiers, because they're not well known, and certainly not well known in the RF community and not in the ham community at all. But they may be, if they can be perfected and maybe able to be modulated for single sideband, they might be more and more common in the future. They certainly have made big headways into the audio market at this point. So many amplifiers now that are used in audio applications are Class D and Class E amplifiers. All right, so I think that's all I have on that. Yeah, that's it. So any questions? Let me stop sharing.
Thank you, Scott.
You're welcome. So anybody have any questions?
That was way more in depth than I thought it would be. Thank you, Scott. I learned some things there.
Well, it's one of those topics where if you don't go into enough depth, you're not going to get the message across. And if you go into too much depth, then it gets really complicated and technical. But the thing is, I just wanted to show you, because we talk about like switch mode power supplies all the time, and the big problem everybody worries about with switch mode power supplies is noise, correct? So we all know that if you get a good one, that's built, well, and it's got good filtering in it, you're not going to have noise problems. And one of the big skepticisms about Class D and Class E is for amplifiers is the noise. People say, "Oh my God, this is going to put out a ton of noise," but if they're done right, they won't. So it's all in the filtering. And the point is, though, that the parts, you don't have to spend a whole lot of money to build these things. So if you were a manufacturer and you were looking into this kind of technology, it probably would be cheaper to build these things than it would be for traditional amplifiers that they put in, what radios we have now. And they're a heck of a lot more efficient. So what it means is, since they're so efficient, they're not going to generate very much heat. You don't need all the heat sinking. You don't have to worry about thermal management as much. And they could be smaller. The actual parts count and the size of the radio can be actually smaller. So you can save money. So that's why I look at it. And that's kind of why I wanted to put it out there. And I thought, we probably won't see these things on the market if at all, for years. So, but if they ever do come on the market, now you can say you've seen it here first. So anyway, I appreciate all your people's patience, and you didn't fall asleep on me. So that's pretty good. Okay.
No, this was great.
Thank you.
All right. Thank you all for coming. We'll try to fix the, I know Anthony's already sent out some emails to help correct the reflector and the reminders. So hopefully we'll have some more folks joining. At the next meeting in January, we will be meeting at Tommy's 4th Street Bar and Grill, Corvallis, Oregon. And if you are listening to this replay and you want to, you're not on the email list, please, send me an email at n0vlr Victor Lima Romeo at arrl.net. And we'd love to have you join us for our holiday in-person gathering.